Okay, scientific notation is sometimes also called power of 10 notation. Okay, what scientific notation looks like is this. I might have a number that looks like this, 1.14 times 10 to the 6th, right? Or 2.29 times 10 to the negative 3rd. Those are both just examples of scientific notation. Does this pattern or this template look familiar to you? Okay, very good. So what scientific notation does for us is it allows us to represent or express really large numbers and really small numbers. Okay, it allows us to represent really big numbers and really small numbers without all these zeros. Right? This would be this number right here. This one would be 11412. Right? That would be that number right there. So it allows us to express these numbers, really big numbers or really small numbers, with more flexibility. A problem with scientific notation is that when we have big numbers or small numbers and we put them into scientific notation, sometimes we can lose some of the precision of that measurement. So let's say I had a measurement that was, I don't know, it's a really big number, 1,647,9,8,4,3,2,1 meters, right? Let's say we had this huge number of meters, right? Probably I shouldn't have measured it in meters if the number was going to be that big, but I did. Okay, so let's say I've got this exact number of meters, but I want to put it into scientific notation, 1.65 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.65 times 10 to the 9th would be maybe how I would do that. And so what this number really represents is 165, oops. Is this number as exact as this one? No, right? It loses some of that precision by putting it into scientific notation. Because by putting it here and saying times 10 to the 9th, we're having to add all these zeros that go with it. We'll walk through how we got to the zeros and how that stuff comes about. But I want you to see there's pluses and minuses, right? Or positives and negatives to putting things into scientific notation. Okay, the good thing about it is it allows us to express really big and really small numbers, but the problem with it is we lose some exactness of that number, right? We lose some of the precision of that measurement. So, okay, here's the template that it follows. Scientific notation always follows the template m times 10 to the n. M times 10 to some n value. Okay, m, which is right here before the times 10, that number has to be greater than 1 but less than 10. Okay, so that number has to be between 1 and 10. So would this be a valid scientific notation expression? No, because that number is not between 1 and 10. Okay, we've got to make sure that the numbers that we express right there at the beginning are always greater than 1 but less than 10. Okay? For my numbers that are greater than 10, when I put them into scientific notation, my exponent's going to be positive. So some people like to try to memorize, if I move the decimal left or if I move the decimal right, here's what's happened to my exponent. I don't love to memorize it that way. Okay, what I'll kind of show you is this. So let's say I wanted to express the number 650,000, and I wanted to put that number into scientific notation. Okay, is this number that I'm trying to express greater than 10? Yes, so the exponent that I use for my scientific notation will have to be positive. Okay, but how do I figure out what my exponent needs to be? Right? Here's my original decimal point. And to get this number between 1 and 10, where does the decimal point have to go? In between the 6 and the 5. So how many spots are between that? 1, 2, 3, 4, 5. And isn't it the same 5 if I go from this way? 1, 2, 3, 4, 5. It's 5 regardless of which way I count it. So that's why I don't like trying to memorize moving the decimal left or moving the decimal right? I'm really just counting the spots. So my number here would be 6.5 times 10 to the positive 5th.
So since you Don't you count the, so on the one?
426 million. Let's say I wanted it in scientific notation with 2 decimal places. Okay, in scientific notation with 2 decimal places. Here's my original decimal. And then between what 2 digits does it need to go now to put it between 1 and 10? The 4 and the 2. And so between that is 1, 2, 3, 4, 5, 6, 7, 8 spots. So 4.26 times 10 to the positive 8th. Okay, how does that feel? Pretty good? Familiar? Okay. If my number that I'm trying to express is less than 1, then my exponent is negative. So that would look like this. If I'm trying to express this really teeny, teeny, tiny number. 0.0000041. This number that I'm trying to express is less than 1. Here's my original decimal. Where does it need to go? Between the 4 and the 1. So now it doesn't matter which way I start counting, but I had to move it 1, 2, 3, 4, 5, 6, 7 spots. So 4.1 times 10 to the negative 7. Times 10 to the negative 7. Okay? Questions with that? All right, let's try a couple here with practice. Okay, I've got a couple practice ones for you on the next slide. Let's put this one into scientific notation with, let's call all of them with 2 decimal places. Sometimes you'll have them with 1 decimal place, with 3 decimal places, whatever it might be. You might have to change that. We'll look at that here in a little bit, but I want to put them all into scientific notation with 2 decimal places. So let's do these first couple together here. Here's my original decimal place, and then here's where it needs to be. So I counted 8 spots that has to move. Is that right? Okay. So if I'm going to put it with 2 decimal places, is it going to be 5.3 times 10 to the 8th? It needs to be 5.31 times 10 to the 8th. Obviously, the more decimal places I put, the more exact my number is going to be. So if I was allowed, I could put 5.31312 times 10 to the 8th. And that would give me the exact same number as that. Right? If I was allowed to put that many decimal places. But in this case, I asked for only 2. Okay. All right, next one here. Here's my original. There's where it needs to be. Okay, we need to understand, especially with these small numbers, we don't start counting from over here. Right? We don't want our new decimal place to go all the way over here. We want it to be between 1 and 10. So right there. 1, 2, 3, 4, 5. So 3.43 times 10 to the negative 5th. Is that what we had? Okay, why don't you do the next 2 on your own? Try the next 2 on your own.
Times 10 to the power of 4.
4 times 10 to the 4th. Okay. I agree with this part, but what are we missing here?
2 zeros.
We wanted 2 decimal places. So what would change there was that this would be 4.00 times 10 to the 4th. Okay. Very good. All right. Kira, what'd you have on the second one?
2.21
To the negative what?
4.
Negative 4. Okay, so how'd you get 2.21? You put it right there? Okay, so here's what it would look like. We need our decimal place to go here. And we move it 1, 2, 3. So I think it should be 1.22 times 10 to the negative 3. Is that what you guys had? 1.22 times 10 to the negative 3. So we're looking for where those digits start, and we're putting that decimal place really between our first 2 digits. Okay, okay, to make it between 1 and 10. All right, let's work the other way now. We've got a number in scientific notation, and let's express the full number that it's asking for or that it's trying to express. So 4.21 times 10 to the third, the positive third. Does that mean we're trying to express a number that's greater than 10 or less than 1?
Greater than 10.
We're trying to express a big number, right? It's greater than 10. So in this case, when my exponent is positive and I want my number to become bigger, I need to move it 1, 2, 3 spots. Okay, and so if I move it to a spot that's got an extra place like this one, what do I add there? A 0. Okay, so that means my final number that I was trying to express was 4,210. 4,210. Okay, so here's the issue with scientific notation is we don't know if this was our original measurement. Our original measurement could have been 4,208 and it got rounded up. Our original measurement could have been 4,210.001 centimeters, right? And we lost that precision of it. We don't really know, but that's what number we're trying to express based on that scientific notation there. Okay. Second one here, this is times 10 to the negative fifth. So do you think we're trying to express a big number or a small number? A small number. So 3.39. We're going to make it smaller. So which way should I move it? Left. So 1, 2, 3, 4, 5. And I put my new decimal there. And then I have to fill in all those gaps with zeros. Okay, so that means I was 0.000339. Does that feel pretty comfortable? Yes. Okay, do the last two on your own. That's what I had on the next two. Is that about what we had?
Yeah.
Yeah. You could put a 0 right there. Yeah. It won't affect our number at all. So either way is totally fine, okay? I, out of habit, just don't. I know math people like to have the 0 there. I don't really care, okay? I don't, but yes, that's probably the more technical way to put it. Okay, any questions with that? I'm going to show you how to use scientific notation in your calculator. So go ahead and grab your calculator out. Have you ever learned how to use scientific notation in your calculator?
I think I just did.
Okay. I'm going to show you a way to use it. And I know everyone's calculators may be a little bit different, but I'm going to show you on mine, and then we'll see. I can kind of adjust things from there. Okay?
Hit second.
Oops.